Doing in topic 12, probability. So 12.1 was more kind of the basic probability, knowing when to add, when to multiply. Today we're going to talk about conditional probability. So finding a probability given a certain condition. Okay, and that's what we're going to look at. So conditional probability. The probability that an event B will occur given that another event A has already occurred. The notation, and what it looks like, it's P of B slash A, and I shouldn't even say slash because it's a vertical line, but what that says is that says the probability of event E given event A. So for any two events, A and B, in the sample space, the probability of B given A is equal to the probability of A and B over the probability of A. So when we're talking here, the probability of event B given event A. The probability of event B happening given that A is true, okay, or given that A has already happened. The basic formula is that you do the probability of B and A on top divided by the probability of A on the bottom. Okay, so that's your basic setup. So we're just going to practice a bunch of conditional probability, help you guys understand the setup, know how to fill it in. And other than that, it's probability, simplify, and go. Okay? So let's look at our first example to work on some understanding. A student committee is being formed to decide how after-school activities will be funded. The committee members are selected at random from current club members. The frequency table shows the current club membership data. Okay, so we have our table. What is the probability that a member of the art club selected at random is a junior? Okay, so first of all, I want to turn that into a conditional probability setup so that I can use my formula here. And so they're basically asking, and you have to read this carefully, but they're asking the probability that the student is a junior given that are a member of art club. Okay, that's the probability we're looking for. Now, in terms of writing it out, and a lot of times they'll have it written out for you, but what we're looking for, or what it would be, is it's the probability of a student being a junior given that they are a member of art club. Okay? So that's what that question is asking in terms of conditional probability. Now, in terms of setup, if we use our formula, okay, and here's what I would think. The formula uses B and A, yes? So if we use that basic setup, think of this as junior being B and member of art club being your A. Does that help you to be able to set up your formula? Okay, because that's basically what we're looking at here. So in that case, probability of A and B over the probability of A. So probability of A and B is going to be the probability that the student is a junior and, I'm just going to write art club, in other words, a junior and a member of art club, divided by the probability of A. What's A? A is your second piece, it's your condition. And in this case, the condition is a member of art club. Okay, that's the setup you're trying to fill in. Now, I'm going to show it the official way first, which to me is a little extra. And then we'll get to the easier, quicker way. Okay, just mathematically, it's a little easier. So on top, let's talk about the top. The probability that a student is a junior and in art club. What do we have happening here in terms of juniors and in art club? So there's 16 students that are juniors and in art club. I disagree with your 58 though.
116 out of
out of the total 115.
I thought it was like out of our club though.
Well, okay, I am just working, as I said, I'm going to kind of take this the official, more complicated way, but then we'll clean it up, okay? You're too far ahead right now, okay? So if I'm just looking at the numerator, probability that a student is a junior and in art club, there's 16 of those students out of a total of 115. So what I'm saying here is the top probability is 16 out of 115. Yes, I'm going to have a fraction over a fraction, but we'll make it better, I promise. Denominator. What's the probability that a student is a member of art club?
58.
Probability that they are a member of art club. There are 58 students in art club out of 115. Now, I know, I told you guys, this is not pretty. I'm going the long way, the official way. What are you guessing is going to happen here? The 115s, they're going to cancel. You want proof? Do a keep, change, flip. If you do a keep, change division and multiplication, and flip, you have 115 on top and a 115 on bottom. Your 115s cancel. With that in mind, what do I end up with? 16 over, I'm going to go with 58. The number was 58. Okay? Now, did Raja have that to begin with? Yes, he did. I said I was going the long official way the first time. Do you have to do the fraction over fraction? No. You can skip straight to how many students are juniors in an art club? 16. Over how many students are members of art club? 58. Okay, you're going to be able to make that skip. Officially, though, I need to show it. Got to do my job here. Okay? What about 16 over 58? You guys are all going to get it wrong and leave it as 16 over 58?
Reduce it 2.
Uh-huh.
8 over 29.
So you have a final answer there of 8 over 29. Okay? So the fact that basically you're looking at these numbers, right? Junior and a member of art club over the art club. You can skip the idea of probability in terms of they're both going to be out of the total number of students. Okay, questions here? Are we good? Okay, so let's try a few more with this table. And we'll, as I said, we're looking at several examples today. Okay, so I just went to a new screen. I still have the chart up there because we need the chart. Okay, probability that a member of the drama club is a sophomore. Now, they've already got the notation written out here, but probably a member of the drama club is sophomore. Drama club is the condition. So this is what is the probability that the student is a sophomore, given they are a member of drama club. So here's your setup. Now, when I go to set that up, words first, not numbers. What goes on top? It's a probability of what on top?
3.
Words first.
Oh, shoot. Sophomores?
Sophomores.
Sophomores in drama club.
Sophomores and drama club, right?
Yeah.
So basically, yeah, sophomores in drama club. So it's officially it'll read as probability of being a sophomore and in drama. So I'm going to write that as sophomore and drama. Over
Drama.
the probability of being a member of drama club. And I get it. You guys may not write the words down when you do it, but we're learning. I want to make sure everyone knows where these numbers come from. Okay, so on top, probability of being a sophomore and in drama.
3. Over 115.
Yeah. Officially it'd be 3 over 115, but what did I say?
Just reduce 3.
You can skip the 115. Okay? And just go with how many students are sophomores and in drama club. That's 3. Over, probably a student is in drama. How many students are in drama? 17. So we have 3 over 17. Does 3 over 17 reduce? No, it's done there. Okay? Middle point. What is the probability that a sophomore is a member of the drama club? So what just happened here? Reverse this, yes? Because now it's not what's the probability they're a sophomore, it's what's the probability they are a member of drama club, given that they have to be a sophomore. Okay. In words, what's going on top? The probability of being what?
In drama club?
Yeah. On top is the probability of being in drama club and a sophomore. So, as he said, a sophomore in drama. What goes in the denominator here?
36.
Words.
Oh, shoot, drama club.
Okay.
Oh,
Sophomore.
Sophomore.
Probability of being a sophomore, because the condition is what's going on bottom. Okay? So, on top, probability that a student is in drama club and a sophomore. Or in other words, how many students are in drama club and sophomores? Out of probability of being a sophomore. There are 36 sophomores. So 3 out of 36, which reduces to
112.
1/12. Okay. Now, a food for thought type question. Is the probability of being a sophomore, given that they're in drama club, the same as the probability of being a member of drama club, given they are a sophomore?
No. No.
No, it's obviously not the same because we just did them and got 2 different answers, right? What's the difference?
Because they're more sophomores than drama club.
Okay. Well, there's 3 dramas and sophomores, right? But,
There's more sophomores than drama club.
okay. And you're comparing to sophomores here. Up here, we're comparing to drama club members, right? Okay. So it all has to do with what you're comparing. So, are they the same? No. That's the simple answer, right? My explanation, I said the probability of a soph given their drama compares sophs in drama to all drama club members. So let me see how. So probability of the first one, a soph given they are in drama club. It compares sophomores in drama or in drama club to all what was on the first one? All drama club members. Okay, I mean, it really has to do with what it compares to. While the other one, probability of a drama being in drama club, given that you're a sophomore, compares, sophomores in drama club to all, and this time it's comparing to all sophomores. Okay? So all has to do with what you're comparing to. And that's where you've got to understand the idea of conditional probability. It's easy enough to find the numerator. You've got to know what goes in the denominator. Okay? Okay. Well, I'm ready to move on from my sophomores, juniors, seniors, drama club, science club, art club. We're ready to talk about coffee and sleeping and Diego. I either said coffee and got smiles or I said sleeping and got smiles.
Sleeping.
Or both. I'm not sure.
I heard Diego.
I heard you.
Or I said Diego and got smiles. Okay, that's not the one I was expecting there. Now, okay, curiosity. You guys hear Diego?
Why do you like Diego?
Are our brains going to Dora?
Yes. Absolutely. Yes.
He's
Or
not
Dora?
cute.
But Dora's here now?
No, it's
No, just Diego.
Diego.
Sorry, guys. We're just talking about Diego.
That's Thomas's celebrity crush.
Wow.
I used to watch Dora all the time.
That,
was
that
like-
you didn't even hear what she said. She said that was your celebrity crush.
Yeah, I heard her.
You're weird.
Okay.
You're weird.
Gosh, okay. I'm a sister child.
I'm also going with he has how many younger siblings?
4.
No.
Yeah,
I-
but
No, it was
I
just you.
chose Dora's like six.
Okay.
Dora and Diego are my two favorite shows.
Okay.
He's still up.
No.
It's possible. Okay. Let's talk about Diego in the sense of how much sleep and how much coffee he drinks. So, Diego wonders whether the amount of sleep he gets is related to the amount of coffee he drinks. For about 10 weeks, he records how many cups of coffee he drinks each morning and how many hours he sleeps that night, rounded to the nearest hour. Based on this data, what is the probability that he gets 8 hours of sleep given he drinks no coffee? And we'll round our final answer to the nearest whole percent when we get there. Okay, so here's what we are looking at. The probability that he gets 8 hours of sleep given he drinks 0 cups. Okay, conditional probability, yes? What's going to go on top in terms of words right now?
8 hours your vote.
Yeah. It's the probability of 8 hours and 0 cups. Or basically, how many times did that happen, right? How many times did he get 8 hours of sleep and drink 0 cups of coffee? Over, okay, here's the one you have to know. What goes on bottom?
0 cups.
Okay, the probability of him having 0 cups of coffee, the condition.
Wait, so what is going to be the second one?
Yes,
That's not mine.
yes. Assuming it's set up in official conditional probability format, yeah, it's your condition. So, okay, what do we know about 8 hours of sleep and 0 cups of coffee?
There's 12 times. Or 12 times.
It happened 12 times, right? Officially 12 out of 72, but I don't need to worry about that. We can just look at how many times it happened, 12. What do we know about 0 cups of coffee?
Having 12 times.
22 times.
22, I mean.
It happened 22 times. Officially, we'd say 22 out of 72, but 22. What do we know about 12 over 22?
That's a 6 over 11.
6 over 11. Now, okay, officially it said we're going to round this to nearest whole percent. So let's see, what's this become as a decimal? 0.
5 of it, maybe? Is it?
Well, the decimal is 0.54 repeating, if I'm correct. And so when I change that to a percent, 54.54%, but we were told to round to the nearest percent, so that is approximately
55%.
55%. So 55% of the time, Diego was able to get 8 hours of sleep, given he drank no coffee.
I don't think coffee correlates to sleep, though.
It does for some people.
I think if you drink it in the morning, then it's fine. But like if you drink it later on at night, then it correlates to sleep.
And again, it depends on the person because some people would say, well, I can have 1 cup of coffee in the morning, but if I have more than 1 cup of coffee during the day, they're done for. Okay? Now, is that most people? No. But I do agree. I think the evening is more impacted here. Okay.
What I thought it said was, how many cups of coffee did he drink in the morning based on how many hours of sleep he got?
Oh,
I don't think
the night before.
Which, rereading it, that's not what it says.
Yeah.
But that would make
Yeah, I get it.
more sense.
Okay, guys. On the back side, we have the concept of how does conditional probability and independent events relate. Yesterday we talked about independent events. Remember, independent events are when 2 events don't affect each other, right? Rolling a die, flipping a coin. They don't affect each other. Okay? Now, the connection here. Given A and B are events, and given that neither of their probabilities are 0, if events A and B are independent, then the conditional probability of B given A equals the probability of B. And the conditional probability of A given B equals the probability of A. Okay, let's get past the gibberish. Let's look at it in simples. Much easier to understand over here, I promise. If events A and B are independent, 2 things must be true. The probability of B given A must equal the probability of B, and the probability of A given B must equal the probability of A. If those 2 statements can be found to be true, then we have proof that the 2 events are independent. If one or both of those statements are false, then, and I think they would either both be true or both be false together, I'm not 100% sure there, but if they turn out to be false, then they are no longer independent events, but they become dependent events. Okay? Now, the second bullet point is just the first bullet point reversed. Okay? It's saying the same thing here. It's just saying if these 2 probabilities are true, or these 2 statements are true, then the events are independent. So 2 things we need to check here. Now, if you start looking at the next problem, it's talking about using the test for independence. So we're going to officially test. In other words, instead of just judging, are these independent events or not, we're going to have official proof. Okay? And I'm going to go to my next screen, because I have room to work. This table shows the vehicles in a parking garage one afternoon. A vehicle in the garage will be selected at random. Let B represent the vehicle is black, and V represents the vehicle is a van. Are the events B and V independent or dependent? Okay? So, I don't want to hear your opinions. We're going to do the math. Okay? So if you go back and you look here, right here, guys, probability of B given A, we need to find that. We then have to see if that's equal to probability of B, so probability of the first item. And then we have to reverse it and check the other way as well. Okay? So, let's start with, what do we have, B and V here? Let's start with the probability of B given V. Okay? What's the setup here? Probability of B given V. On top, you're going to do the probability of what? Black and van. This is still our conditional probability. Over the probability of, what do we do with the condition? Van. Okay. Go to our chart. Probability of black and van. How many times does that happen? 3. Over probability it's a van. There are 3 vans. What do we know about 3 over 3? It's 1. Now, what do we need to compare that to find out this is an independent event? No, not. Probability of B given A needs to equal probability of B. the first piece, not the condition, but the first piece. So in the one we're looking at, we need to find the probability of B. So we're comparing the probability of black given their van to just the probability of black. What's the probability of black here?
13 out of 22.
13 out of 22. Yes? Okay, guys, what do we know?
That they're not equal.
Those are not equal. We just found that the probability of B given V does not equal the probability of B. Now, could we essentially jump to our answer now? We could. Okay. I'm going to go ahead and show you the other way, because officially it has to be false. It can't be, needs to be false one or both ways. But I want you guys to see here. So now what are we going to do? We're going to reverse. So now instead of probability of B given V, we're doing what? V given B. Probability of V given B means on top I'm going to do probability of vans in black again over probability of the condition, which is B. And I'm honestly not sure what you said, because B and V are horrible to be in the same problem, aren't
Yeah,
they?
it should be like X and Z.
And I understand B and V because they stand for things, but okay. What are the chances of having a van that is black? There's 3 of them. How many black vehicles?
Oh shoot. 13.
13. So that's 3 out of 13. What do we need to check?
The probability of B.
Probability of V. Probability of the original probability just without the condition. Probability something is a van.
3 over 22.
We have 3 vans over 22 vehicles. What do we know?
And it's not equal.
3 out of 13 and 2 out of 22 are not the same. So probability of a van given it's black does not equal the probability of a vehicle being a van. Thus, what can we say? These events are, what did you say?
Dependent.
Dependent. They are not, because there's a test for independence, it failed the test. So events B and V are dependent. Okay, and that's your proof to show it. Okay. Now, if you think about it, does that make sense? There's only 3 vans, and they're all black. They can't really be independent of each other in this scenario because
That means that
they're all the same.
that'd be all the cars in the garage.
Yeah. So, okay, let's try another. Let R represent the vehicle as red, and C represent the vehicle as a car. Are the events R and C independent or dependent? Explain. Which, my work is my explanation, in my opinion. Okay, what are we trying first?
B. parentheses, C, or R, C.
Okay. So the probability that a vehicle is red, given it's a car. On top for conditional probability, you put
Red car.
both red cars. On bottom for conditional probability, we're going to put probability it is a car. What do we know about the probability of being red and a car?
Fine.
There are 5. What do we know about the probability of being a car?
11.
There are 11. 5 11ths. What do we have to compare this probability to test for independence?
P, parentheses, R, parentheses.
Okay, the probability that it is red. So we're just comparing the initial probability just without the condition this time. What is the probability a vehicle is red?
7.
I have 22.
7 vehicles out of 22. What did we just find out in this scenario?
That is dependent.
Hello. No, but I will. From the office, I assume, right? Okay. Bye. Okay. So right here, probability of red, given it's a car, does not equal the probability of it being red. Now, what is that looking to send us towards, unless we made a mistake? They're not independent. What's the other test we do?
P, C, R.
Okay, probability of a car, given it's red. Might need a different color here. So on top, are you getting to be pros at conditional probability? I hope so.
Inside.
On top, it's both, right? The probability of car in red divided by, what do we put on bottom in the conditional probability? The condition. So the second piece, R. How many red cars do we have?
Same.
How many red vehicles do we have?
7.
Okay. For our independence test, what do we compare that to?
P, parentheses, C.
Probability it is a car. So you compare it to the original probability. What is the probability of having a car?
11 over 22. Which one?
11 over 22, which is indeed 1/2.
Which is not equal.
Which is not equal, which is kind of what we expected, right? Probability of a car, given that it's red, does not equal the probability that it's a car. And so we know these events are dependent. Okay.
Sorry, I'm just tired. I know you were sleeping.
Now, we have one more in this section about conditional probability. You want to try and get through it?
Yes.
Let's try.
trying to
Okay. Different scenario. We're still talking about independence. Okay. The table shows data for the junior class at a high school. A student from the junior class is selected at random. Let G be the event that the student is a girl. Let F be the event that the student is taking French. Are events G and F independent or dependent? Okay. What are we finding first? Probability that is a girl given she is taking French. What's the probability? A girl given she's taking French. On top, it's going to be what?
4 or 5.
A student that is a girl and in French, divided by probability the student is
French.
in French. That's the condition. How many girls in French? 45.
Oh, shoot. Yeah, 45.
How many students in French?
75.
Well, I know they both divide by 5 at least.
So it's 9, 15.
Should be 3
Mm.
fifths.
Yeah, 3 fifths.
That means I would say that means it divides by something bigger than 9. That divides by 15. Okay, so 3/5. What are we comparing that to?
FG. Or no.
No.
G. Or
Probability
PG. PG.
the student is
A girl.
a girl. In this scenario, how many girls do we have?
Oh,
300 girls out of
500. Oh, that's
500.
That's 35.
300 out of 500 is definitely 3 out of 5. What did we just discover?
75.
Possibly. Both have to work for it to be independent.
Oh, shoot.
We discovered that the probability of a girl, given she's taken French, does equal the probability of a girl. Now, as I said, you can't assume yet. So, now we've got to do it the other way. Probability, a student is in French, given they're a girl. On top, it's still probability of a girl and French,
French girl.
but this time, probability of the condition,
Oh, shoot. G. It's G.
which is girl.
Oh, my goodness.
Now, on top, girls in French was already 45. Probability the student is a girl. How many girls?
300.
300. 45 over 300. Divides by 5, probably bigger than 5.
9.
So divides by 15 again.
320.
Yeah, he said 3/20, so I'm going with it. I'm believing.
Calculator said 320. Yes.
Hey, my notes, my answer key says 3/20. What am I comparing this to real quick?
French.
Probability of a French student.
7 over
How many students taking French?
75 over 5.
75 over 500. Divide by 25,
You get 3.
and you have 3/20. Guess what just happened?
Equal to everything.
Okay, the probability of a French student, given they're a girl, equals the probability of a French student. And so, since those are equal, these are independent events. Okay, tomorrow we'll talk about the backside. If you didn't get 12.1 done, go in and get it done.